Alright, let's finish up these slides on Boolean algebra. So, we talked about how to simplify stuff using the rules, just rules of logic with new symbols, and let's get into some fancier gates now. Let's talk about two gates called NAND and NOR, okay? They are what's called functionally complete, which is fun to think about. So, let's talk about what that term even means, right? So, if you have a bunch of operations in Boolean algebra, they are called functionally complete if you can represent any Boolean function, any truth table, essentially, using just those operations, okay? So, for example, one example of a functionally complete set of operations is addition, multiplication, and complement. So, and, or, and not, you can create every single truth table using just and, or, and not. You remember this, right? Like, you can get rid of the implication because this is just not P or Q, right? So it really does work. You can make anything out of and, or, and not. And there's more than just that. You have options other than those, okay? But this is one functionally complete set. Some cool ones are NAND and NOR. So if you ever, I don't know, create a circuit manufacturing company, you are going to fall in love with either NAND or NOR because you can just mass produce a single gate and make anything ever, which is pretty cool. So yeah, NAND by itself is functionally complete. The set containing just this operation called NAND and the set containing just the operation called NOR. Those are functionally complete just by themselves, which is crazy to think about. All right, and here's NAND and NOR. Here's how you draw it. Here's the circuit, what it looks like. So it's AND with a little dot. And here's NOR. It's OR with a little dot. And all NAND is, here's the symbol for it, it is take the AND first and then negate the result. Same for NOR. Take the OR first, then negate the result. So it's like, all right, take the AND first, negate. Take the OR first, negate. And that's why I taught you that circle means negation. That's how you read those. And yes, so here's the truth table for NAND and NOR. They look weird because we haven't seen those before. It's just negating the x ANDed with y case. This is negating the x ORed with y case. Okay? So that's what's happening there. And it's crazy to think about, but you can make anything out of just NAND. You can make and, or, and not. You can make, well, this is or, right? Or, and not. Out of just NAND by itself. Same for NOR. Each of those by themselves are functionally complete. So if you want to build any truth table, any circuit, you just need a bunch of NAND gates. That's all you ever need. Or if you prefer NOR, that works as well. So let me prove this for you. Let me at least show you that you can make complement out of NAND very easily. So like, if I want to negate x, that is equivalent to negating x ANDed with x because of the idempotent law that we used so many times last time. Oh yeah, that's totally, that simplifies to just not x by itself. And what do you know, this is x NANDed with x. Hey, so that's how you can make complement or negation, whatever you want to call it. And you can do the same for addition or multiplication, which is your AND. Okay? It is possible. These are functionally complete. All you need is a bunch of NANDs, and you can make anything. And so that is good if you want to scale up your fabrication process. Okay? So that is NAND and NOR. Let's talk about something that you are already familiar with because I forced you to learn about it early in a lab. So Boolean satisfiability. Okay? So given some Boolean expression now, we say that it's satisfiable, right? If there's a way to make it true. In Boolean algebra land, it's make it evaluate to 1, right? So we want to find some combination, some setting of the input variables to either 1 or 0 to make the final output a 1, okay? And this is a very surprisingly hard problem to solve. If you want to determine the satisfiability of an arbitrary formula in Boolean algebra, CNF is usually what people work with, so a CNF formula, conjunctive normal form, that happens to be NP-complete, if you've heard that term before. If you haven't, it just means that it's a very, very hard problem to solve, okay? And let's talk about it. So, yeah. The best algorithms, in fact, that we know to perform the satisfiability problem, including the one that you implemented in your lab that I taught you, was exponential time, okay? So we had like, here is some arbitrary formula in DNF. If I gave you a formula in DNF, it's very easy to read off when it's true, right? But that's not always the case. CNF, it's very hard, okay? So that's one thing that I want to say. If it's an arbitrary formula, it's probably easier to make it CNF than DNF, and it's going to be O of 2n to try and solve it, where n is the number of variables that exist in the formula, okay? Because you have to try every combination of possibilities, true or false, right, for each of those n variables. So you coded up an exponential algorithm, in fact, in your lab. Did you notice that? So yeah, the best we can do for this problem is an exponential time algorithm, assuming p is not equal to np, if you've heard of that, okay? So yeah, let me give you the just the very short lower division version of this problem, and you will definitely revisit it later in like an algorithms class or a computability theory class. So P, these are sets. P is the set of all problems that are solvable in polynomial time. And polynomial time is like, well, here's P. It's a cloud. P is like, it contains O of n squared. Those are all polynomials with a number, right? N cubed, things like that. And then NP is problems that are easy to verify in polynomial time, which is weird to think about. But like, if somebody gave you an answer to satisfiability, it's very easy for you to check if it actually worked for the formula, right? You just plug it in. You only have one thing to try. It is linear time for the formula to check somebody's answer, but it's very hard to find that answer, okay? And so because of the way this is defined, it's actually not clear whether there is any overlap between these two sets of algorithms. So you'll win $1 million if you can see if there's any overlap between P and NP, okay? And this is a NP complete problem, satisfiability. Cool, huh? So, all right, that's enough for that. I'd be happy to talk about this more in office hours, but it's a fun thing to think about. I'd like to teach you about TicTacToe now and satisfiability, okay? Because satisfiability is a very important thing to use. You've used it already for your lab, but let me give you another way, another example of it so that you can see how useful it is and how general it is, okay? So let's play TicTacToe and turn that into a satisfiability problem, okay? So here is the way we're going to encode it into a satisfiability problem, because it needs to be, we need a way to get back true or false, right? So we need to ask a yes or no question, or a, like, what ways are there to make this a yes answer question? So here's the question that we will ask to our SatSolver. We will ask, what ways are there for x to win, okay? So let me show this to you. So like, we want to express the fact that, yeah, here's one way for x to win, for example. Dun, 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 dun. That's the idea. So what we have to do is make logical variables for the board, okay? That's the first step. And we're going to feed this off to an industrial strength SatSolver. This is going to be exciting. So B11, B12, B13. This is B21, B22, B23. So we're going to make 9 different variables. B31, B32, B33. And each of these are going to be set to, we can think of them as being set to x or o, right? That's the goal. And eventually we'll have the SatSolver think that it works like this. But here's how we can encode the rules of TicTacToe now that we made 9 different variables and they're supposed to represent this idea. Our next step is we need to represent when, or what the board looks like. Looks like when the game is over, first of all. So what's an ending state? That's the first thing you have to encode. When the game is over. And when x won as well. Okay, that's what we want to find. What ways are there for x to win? And there's a way to turn this into a SAT solving question, believe it or not, this idea. And so it is a very general concept, and it is very useful. You can solve a lot of problems using a SAT solver. So yeah, here are all the constraints that we want to be true all at once when the game is over. Okay, these are the constraints of the desired boards at the end of the game. So the first constraint is that every square is filled with x or o. Okay, so that's the first constraint. We need to make sure, and you can actually encode this in logic. You can be like, okay, x is the number 1, o is the number 2. Just make sure that every one of these variables is set to either 1 or 2, something like that. And of course, you can encode arbitrary numbers as a bunch of individual Boolean values. Crazy. All right, it all becomes true or false at the end of the day. So that's one thing we can encode for every variable, this for all statement. We also need to encode the fact that there is one more square filled by x than by o, because we're assuming that x goes first. Okay, that's just without loss of generality. We can always assume that x is the player who goes first when they play the game, and so that's how we're going to ask our question. So we can ask that the number of x's in all of these variables that have either been set to x or o adds up to 5. Cool. So again, we're using numbers and we're encoding that in terms of Boolean operations somehow, but it is possible. The SatSolver takes care of it. Crazy. And then we also want to represent the fact that x won and o did not. So like we're here, but not potentially also here, x, o, x, o, 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 right? Because here x won and o won. We don't want that. That makes no sense. We don't like that. Okay? So we want to encode only valid game boards. So something like this. So make sure that x won. So one of these cases is true, right? Either like it won the rows or the columns or something. And it's not true that O won any of those. Like, none of these were always the same, okay? So this is a bunch of logical operations. That's all I'm trying to say here. We're trying to build up a bunch of little logical operations, and we can represent TicTacToe based on it, okay? So you can actually feed this to a SatSolver. The most powerful SatSolver these days is called Z3. It's made by Microsoft. And here is our SAT solving program that I have made ahead of time because it's quite complicated. But this is what it looks like. Here's the kind of syntax that it uses. Oh man, it's essentially Racket. And here is our TicTacToe game that we can run in Z3. Okay, so we're going to represent x as 1 and o as 0. And then here is me declaring a bunch of variables. Here is me counting the number of x's, counting the number of o's. Here is me checking if x1 or o1. And here are all the constraints now. So make sure that x has 5 places on the board. Make sure that o has 4 places on the board. Make sure that x1, remember that x is the number 1, o is the number 0. Make sure that o did not also win. And then SatSolve. And show me values of variables, please. So if I click execute, here is a very long output, and peppered within the answer are values for these variables. So it's like, okay, b12 is 0, b13 is 1, and if we draw this, if we draw the answer we got back, we have a valid game board, one way for x to win. And we can have it go back and try other options as well. But we'll just do the first one. So b12, that was this one, and it set it to 0, which is O, which is nice, good for me, because I can just draw a 0 and pretend it's an O. And then b13 is a 1, so X. b32, it's weird the way that it's ordering this, is a 1, 1, 2, 3, 2, x. And b21 is a 0, 2, 1 is an O. So b33 is an x, okay. b23 is an O. b11 is an x. All right, how is x going to win? Let's see. b31 is an O. Oh, okay, it must be the diagonal then. And b22, yes, the middle one. That's a 1. And so we just had a SatSolver solve how to, technically all the different ways to win tic-tac-toe. It just gave us back one way, though. We can ask for all the others if we'd like. So, yeah, you can seriously encode any problem, most problems, in terms of Boolean satisfiability, including things that involve numbers or characters. And yeah, it's a very useful thing to want to do. So it's a bit more powerful than you might expect, and that makes sense because it's a very hard problem to solve. Okay, most things can be transformed into it. So yeah, that's all I wanted to show you about sat solving. It's just it's an important thing. It is useful, and hopefully TicTacToe helps you notice that. And excuse the weird looking edit, but I did want to just briefly show you a bit more about the syntax for this racket-like syntax for using a SatSolver. Let me show you what's going on under the hood and how it's actually transforming all of this stuff, or what it's trying to do with these expressions, and how they might become like true and false under the hood. Okay, so I told you, like, here are the variables. We're making a bunch of variables to represent our game board, and here is how it's counting all the x's. There is something that you can encode. You can encode math, first of all. You can encode addition into Boolean algebra, believe it or not. I'll talk about that more at the end of the slides today. But you can encode addition of numbers as a Boolean formula. You can make a circuit that does it, actually. It's really, really cool. So this is how you count every x. So it's doing, this ITE stands for if then else. It does an if statement. It sees, hey, is b11 equal to 1? So it's like checking the binary digits, all the bits of the b11 variable, which is an int, and making sure that only the last one is set, making sure that the whole thing is a 1. Crazy. And if it is a 1, then I want you to give back a 1. Otherwise, this is like the else case. I want you to give back a 0. All right, so it's if it's set to 1, which means x, that means give back a 1. And as many times as there is an x, it's going to give that many 1s back. And so that's how it's adding up all of the x's on the board. Okay, that's how we encode that to the SatSolver. It knows about addition. It knows about if then else. Crazy. That's like implication, right? So it knows how to encode that too. But numbers are the weird thing. It's totally capable of it, though. Then we have, we can make this even bigger. Same thing for O's. Count if it's an O, that's if this digit, or not the digit, but the place on the board is equal to a 0, because we're having 0 represent O. Okay? So count how many times we see 0, and give back a 1 each time. Add together every time we saw the O, and that is the number of O's on the board. Cool, huh? And so that's the first bit of constraint. So we have to make sure that x went first, so there's one more x on the board than there were O's. And so this makes sure that the board, implicitly, it makes sure that was filled in, because there's 9 variables total, right? They have to add up just like this. So that works out quite nicely for us. And this is a nice little helper function to the SatSolver that helps us encode and ask for who won. Okay? So here's how you ask for who won. It's just, these are actual logical operations now, so we're doing a bunch of ands of ors. So somebody won, the player who you passed along, won if the player was in every single one of these rows. Like, this is the first row. b11 was equal to b12 was equal to b13. If that's true, then somebody won. And that person that we were asking, the player, if the player was in all these places, then they won. Does that make sense? So that checks the first row, the second row, the third row. This is the same for columns. If b11 is equal to b21 is equal to b31, that's checking, hey, are all of these equal? If so, yeah, we won. Okay? So try all these possibilities, and then the diagonals are when the numbers are the same, or they differ by 1 each time. So yeah, if any of these things were true, so OR them together, then that person that we were looking for, we were trying to see who won, they won. Okay? So maybe we're asking for X, right? We're going to eventually ask for X. Like the player is set to 1. Hey, is B11 set to 1? Is B12 also 1? Is B13 also 1? Because X is 1. If so, then yes, we found that X won this particular match. And so that helps us encode who won, and then the SatSolver can go and find all the ways to make that happen. Do you see that? So it's really doing Boolean operations at the end. Checking for equality is something that can be translated to a Boolean operation, and same with and OR, of course. Those are already Boolean operations. Okay? And yeah, it's these asserts that tell it, here are my constraints that I want you to enforce, please. Okay? And that is a better explanation, I would say, of what's going on here. So back to past me now. Let's move on to Kmaps. All right. The next thing that I want to show you is a way to help you as you simplify formulas. A little trick, a technique is called using a Kmap, which is short for Carnot map. Okay, that's a person's name. And it's just a nice box with little boxes that you can draw to help you simplify that expression. Okay? The idea is you start with your truth table, instead of like working this way and being like, okay, let's see what happens when x is 0, y is 0, x is 0, y is 1. Let's fill everything in and kind of somehow simplify that way. No, instead, let's write it all out in a form that lets us like circle common things and use our pattern recognition skills as humans with eyes. Okay? So yeah, instead of using a truth table, you turn your expression into a truth rectangle. Crazy. And you look for patterns. Okay? So what you do is you write 1s or 0s, true and false, inside of here, and you start circling groups of 1s, though the size of those groups is forced to be a power of 2. So the size of that group of 1s better be either 1, 2, 4, or 8, or bigger, if you have a long enough table with multiple variables. And the groups that you circle better be rectangles or squares. You can't make like random looking things. You can't like circle, okay, this is my group of 4. It's the Tetris L piece. No. It's got to be like this. You got to circle it like this, or like this. No, sorry, like this, like this. Groups of powers of 2, right? So this is valid. This is valid. I think you get the idea, right? You can also circle individual boxes. That's always fine. Yeah. And notice that this grid is not the normal ordering of values. It's like, okay, A is false and B is false. A is false, B is true. And now suddenly they're both true? That's usually at the end, right? And then A is true and B is false, that case. So these cases are in a very special order when you make this table, and you have to remember that order. You can't use a different one. The notation looks like this. The order goes, that you have to write it as each adjacent cell, so like this one becoming this one becoming this one, it better differ by just 1 bit. That is the only way that this trick that I will show you using these Kmaps works. Okay? Each adjacent cell must be different by only 1 bit, so just remember this order. I'll give you this order on your homework, so don't worry. So yeah, only one thing has changed. B has been flipped. Only one thing has changed between these. A has been flipped. Only one thing has changed between these. B has been flipped again. Okay? And then, of course, these are in the proper order. There's only one variable. Okay? So that's our example rectangle. And like here is an example of me drawing stuff. Let's pretend that we filled it in like this. Like when A and B and C were both false, it was a 1. When A was false, B was true, and C was false, it was a 0, and so on. So let's draw as few groups as possible. Can you do it? So I think there's a couple ways, actually. But the best you can do is draw 3 boxes, right? So, like, here's one. You're kind of forced to put this one by itself because you can't draw Tetris pieces. Here's another. Box of 4, that's nice. And then here's a box of 2. Okay, so that helps us simplify this formula, and I'll show you why later. Okay? So hopefully the process makes enough sense. You just fill in the table from your formula/truth table that you were given, and you look for patterns, okay? You circle groups of 1s, and the groups better be of this size, powers of 2 size, and they better be rectangles or squares. After that, it is quite nice. And I'll show you how this makes it very easy to simplify things, okay? So, let me show you this. So let's use a Kmap to fill in the truth values for the following expression. All this. So we're given in DNF. Thank goodness. So it looks like the formula is true when A is false, B is true, and C is false. So A is false, B is true, and C is false. So this case is a 1. See how I'm reading that? Then this case is also a 1. So A is true, B is false, C is false. That's another 1. Oops. And then we have this one, A is true, B is false, and C is true, so this time we have this one being a 1. And then one last one, A is true, B is true, and C is false. That is another 1. Okay, so those are the only 1s, the rest are 0s in the formula. That's essentially converting that to a Kmap instead of a truth table. And now, please, how would you make your groups? Okay, use a Kmap to write a simplified version of the expression. Let's first find groups of size powers of 2 that are rectangles. Okay, how would you do it? Think about it for a second. And what do you know? It is the best you can do is 2, right? 2 groups of 2. Circle these guys and circle these guys. You see that? And now let me show you how to simplify after you've drawn these groups. The trick is to look at, the trick is to pick out a single expression for just this group and an expression for just this group. And we need to determine what that expression should be, okay? And the trick is to look at what is in common among everybody in this group, okay? So what is in common among A, B, and C? So it looks like when we're in this group, A can be either true or false. So A is unimportant right now, but it looks like B is always true and C is always false when we are right here. And that is what we needed. That tells us, okay, this group is represented by B being true and C being false. You see that? That's how I can read this. That's the trick. You just find what's in common, and that is your simplified form, okay? And then let's do the same for this. What's in common? So it looks like A is always true, B is always false, because they share this column, right? And then C is helpless, or C is useless. It does not help us here because it can be either true or false, so we're not going to include that. It could be anything. So it looks like A is true and B is false. That's what's in common here. A and B bar. And so if we're in either of these cases, that makes this table. And you see how we simplified it. We just have, well, it's again DNF, but it's a lot simpler. Only at most 2 variables being multiplied together. You see how useful that is? So that's how you use a Kmap to simplify things, okay? And so you always look for what's in common, and that lets you read off the right formula. Okay, so now I want you to try this one yourself, and we'll come back and we'll do it together too. Okay, so simplify this expression using a Kmap, using this same idea. Okay, so let's fill it in. So we have a box. Maybe I'll make the box green and I'll draw it in with blue. So here's my box, 4 by 2. and it goes, oops, it goes C bar C, and then it's always A, B bar, A bar, B bar, and then A bar, B, A, B, and then the one that we haven't done yet, which is A, B bar. Okay, so now we fill in what's going on here. When is it true? When is it false? So what does this make true? It's true when A is true and A is false at the same time. Are there any rows that have that ever? And the answer is no. This actually does not make up any of the answer. Okay. So let's see what's going on there. So this one does not give us anything. So it's already able to be simplified. Okay. What about this one? BA. Yes. Whenever that's true. Dun, dun, dun. So that is true here. It's true here no matter the value of C, right? So we have a 1 here and a 1 here. Does that make sense? So that makes sense there. That can be placed there. And then BA bar, that's this one. It's true whenever this is true, and that's under this column. C doesn't matter. So again, more 1s, right? And then finally this one, C and C bar. That's never the case that those are both true, right? C and C bar both being true at the same time. That's impossible. So that makes the rest of these 0. Okay? And so you might think, you might be able to read off and notice, like, okay, that's going away, those don't make sense. And like, the answer must be this then. Okay? You might think that the best answer is just BA plus BA bar, right? Just the two things that weren't useless information. But you can actually do better than that. Because look at what we can do. We can draw this one box, and then we pick out what's in common. C's can be anything that's useless. A's can be anything that's useless. Oh, the B's were in common. Ooh. B. The simplified expression is just B. It's always true when B is true. You see that? See how you can read the table and understand that now? Yeah, it's only ever a 1 when the B is not complemented, when it's a 1 itself. That is the most simplified version of this. Isn't that cool? So yeah, Kmaps will save you some time. Use them. All right. So yeah, in the last bits of this lecture, this is, I think, as much as I want to do before I release your next lab. So definitely go and watch that video next. I want to give you a taste of what's going to happen in CSCI 45. Okay, so these circuits are going to come back to haunt you, and we're going to talk about them in depth there if you have not already taken CSCI 45. So yeah, I'm going to try and answer this question, like, okay, what is the point of using these circuits? Like, is it really the same as hardware? The answer is, in fact, yes. Our computers are nothing but giant circuits, just a bunch of and, or, and not gates all together, okay? Or a bunch of NAND gates, really, but we can think about them as and, or, and not gates. So, all right, let's think about how we do this. Like, how in the world, like, does somebody make a real computer out of a bunch of little tiny gates? How does that give us computation, okay? And so let me give you one example of this, all right? And hopefully you'll use that and believe me for now until you take CSCI 45 why this all works, okay? So here is an example of a circuit that adds numbers, okay? Because that's probably the most important thing you care about. Like, how does a computer perform computation on numbers? Like, how is that encoded as a bunch of gates? And let me show you. So this circuit helps you add binary numbers, okay? And let me kind of give you a taste of what it's doing. Let's add some binary numbers for fun. 1, 0, 1, 1, 0. Let's add that to 0, 1, 1. Let's see. Or how about just 0, 1, 0, 1, 1 or something? Sure. That'll do. And so if we're adding binary numbers, look what happens. 0 plus 1, that is just 1, that's fine. But 1 plus 1 in binary, that is 1, 0, right? That's 2. We have to carry. We have to carry already. So this makes 1, 0, we carry the 1. This makes 1, 0, carry the 1 again. 1, 0, carry the 1. And one last 1, 0. You see how I'm adding binary numbers? And so, look at what happens. Look at how we can translate this to a gate, okay? Because it turns out that XOR, this is called an XOR gate. It looks like OR, but it has another line. This is the XOR operation. And XOR, surprisingly, is really good at doing 1-bit addition. Let me show that to you. 1-bit addition of A and B. Let me show this on the next slide. So let me show you what's going on here. So if I have, I don't know, X and Y, or I can keep it as A and B. Why not? A and B. And then A XORed with B. Let me show you how the XOR operation is doing addition, really. So let's just use trues and falses, because we know those best. XOR, it's only ever true when they differ, right? So it's true here. And remember that these are zeros and ones, right? 0, 1, 1, 0. This was 0, this is a 1, right? Look at how this is 1-bit addition. If you only had a single bit to work with, well, 1 plus 1 really is 0 because you had to carry, right? The answer is 0, though, in that place. 1 plus 0 is 1. 0 plus 1 is 1. Isn't that so cool? And 0 plus 0 is, of course, 0. XOR does addition on a single bit. Isn't that so cool? Wow. And so that's what this bit does, this part. This is called a half adder, by the way. Because what needs to happen next is we need to work with multiple bits, so we have to sometimes carry from our current operation into the next operation. And we always wanted to carry if those numbers were both 1. So we'll use an AND gate to determine whether or not we should carry a number. Does that make sense? 1 if we need to carry. And you can build up arbitrarily long addition processes on binary numbers now. Need to carry. This is just so nice. It seems magical, right? So yeah, this is how you can use it to add binary numbers. And so let me show you that in action. Let's pretend like we're originally adding 1 and 1. Those are our first bits that we're adding together. Well, the sum is going to be 0, but we are going to carry, right? This is an AND gate. We're going to carry the 1. And the idea is we have to, for the next bit, not use a half adder, but a full adder, because sometimes we actually have 3 numbers that we're working with. A full adder has a carry in as well as a carry out. Okay, that's all. So here's how the process would work. We're just chaining a bunch of the results of carry outs to the carry ins to the addition. So it's like you're doing XOR with 3 things now. So pretending like this was a 1 and a 0 for the next 2 bits. We still have the one that we're carrying, and so we have to do our output, okay? So the answer is 1 plus 1 plus 0. So it's 0, and we are going to carry in a new way, okay? So it's going to be a bit different. But yeah, this works, totally. It totally works. 0, 1, this gives me a 1, the carry is a 0. And if you wanted to make like a full adder, you'd have to chain these together in a certain way, okay? Maybe think about why or how, and feel free to look it up. So that is how you can do numerical stuff with circuits, with Boolean algebra. It is all possible, and it is beautiful. Okay? So everything really is, at the end of the day, a bunch of giant circuits doing all of the computation, showing you this PowerPoint right now, letting you hear my voice. Crazy. So yeah, that's as far as I want to go right now. I am going to make a video for your lab now, so please go and watch that. But you are now all experts on Boolean algebra, which is really just logic all over again, right? With different symbols. But now you know the symbols. So I'll see you in the lab video.